First of all, Eli Howard, who's the Executive Director of Technical Services for SMACNA. Eli's been with SMACNA for over 25 years. Actually, how many years is it, Eli?
March 18th, it became 30.
30 years. I knew it was closer to 30. So. He's responsible for all SMACNA technical standards, manuals, and guidelines for the HVAC, industrial, residential, and architectural sheet metal industry. In his role, Eli has additional responsibilities as both a voting member and liaison to other national standard developers in the industry, such as ICC, NFPA, and the list goes on and on. Eli and I have worked together for many years, and it's an honor to have you here, Eli. We also have Jeff Parks here. He's wonderful. He's a senior project manager for SMACNA with the Technical Resources Department. He has over 30 years of experience in the sheet metal industry. His background includes completing a union sheet metal apprenticeship program and working in shop fabrication, CAD, BIM, estimating, project management, and senior leadership at a major East Coast sheet metal company. So welcome, both of you. Thank you so much for being here. We're really excited about this three-part series. You guys can take it away.
Great. Thank you, Christine. Thank you, Carmen. For everyone in attendance, the first two things I want to ask for is if you have any great hockey players you want to send to the Washington Capitals, please do right now because we're out of the playoffs. We didn't even make it. Number two, if you got any great baseball players, which I know you have out there, please send them to the Washington Nationals because we're teetering on being a AAA baseball team. So we're looking for any help we can from the West Coast. And later on this year, I'll probably get back in touch with you for our football team. Send us any football players you have from any of the great colleges in California. Please send them back here to Washington so we can start winning and going to playoffs again instead of being the butt of jokes of our sports franchises here in the DC area.
You can have Artie Moreno.
Pardon me?
You can have Artie Moreno.
We'll take anybody. Anybody's better than what we got right now. Okay, what we're going to do today is go over our duct construction standards. Myself and Jeff are going to kind of tag team this as we do a presentation. We've done these, Jeff and I have done these for the last 3 years numerous times on Teams and Zoom on the tag team approach. So if you have questions, you go a couple different ways. We can if you type them in, usually one of us is watching that, and we can address the question right then and there. Or if you want to wait to the end, we'll handle them that way. If we happen to see a hand raised up, we'll try to get it that way also in the Q&A. It's going to be a pretty good program. We're going to walk you through our rectangular side of the duct construction standard, try to get into some issues related to hangers, supports, some of the round information we have in there over the next hour plus. Hopefully this will be exciting for everybody. We do this a lot. We like doing it. We like trying to teach people some of the new things in the duct construction standard. And we've got a couple of things we'll talk to you about also today about some unique things that are in the standard that a lot of people don't always remember. But I'm going to introduce Jeff here to get us kicked off. And then I'm going to be chiming in, and you'll hear both of us during the entire presentation. And once we get the screen lit up here with our program. So Jeff, you want to unmute and throw up the program?
Got it. How's everybody doing today? Hopefully good.
Right. Let's see if we can get this roll.
Nope. Sorry. We already thought we fixed this.
We'll just readjust. And while Jeff's going through that, I just want to let you know we were on another call just a few minutes ago with the Uniform Mechanical Code Committee, which is starting to put stuff together for the 2030 Uniform Mechanical Code cycle, which then basically is adopted by California into the CMC. I'll let you know in advance, and we're going to kind of bug all the chapters in California that the call for proposals Any code change proposal must be submitted in by January 8th of 2027. We're going to send some notifications out from SMACNA National that'll be exclusive to all of our California chapters, letting them know that the code change window is open for any proposal. We're going to be submitting proposals with SMACNA National. We are voting members of this committee, so if there are proposals or changes you are looking for in the Uniform Mechanical Code, please share them with us. We'll push them through on our side as voting members to try to get those up to the docket for the Mechanical Code Committee to discuss at their in-person meeting, which will be in May of next year. But January 8th, 2027 is the last day you have a shot to get things in for the next code cycle, which will be the 2030 cycle at this point. I just want to give you a heads up on that. We just came out of a meeting with that Uniform Mechanical Code Committee.
All right, so it looks like I got everything squared away, so hopefully
if I could interrupt real quick, Eli and Jeff, I know you guys are in the same room, so one of you who's speaking, the other needs to mute because we're getting really bad echo when you're both have your microphones open. Thank you. Thanks.
All right, hopefully you guys can hear me fine. Everything looks good on my end, on your end, I should say. All right, good deal. Okay, so like Eli mentioned, we're going to go through the HVAC duct construction standards. This is what we consider part one, going through rectangular duct construction. So let's get started. And here we go. Second. So HVAC duct construction standards, part one, topics. What we're going to review here. Rosen. Limits and proper application of various joints and seams. The use of the manual to determine proper construction options. The types of construction options that are laid out in the duct construction standards. Looking to select the proper gauge, and that's going to be based on, you know, the duct size, the pressure class, and all that's laid out in the duct standards. Selecting the proper reinforcements. And for this first part, we're going to look at external reinforcement only, which would be angle. So information required for duct construction. Comprehensive duct layout indicating the sizes, design, airflow, pressure classes, and the routing of the duct system. The types of fittings to be used based on the designer's calculations of fitting loss, you know, whether that's a square versus 45-degree entry tap, conical versus straight tap, and so forth. The use of turning vanes or splitter vanes. Locations of access doors. Locations and types of control and balancing dampers. The location and types of the diffusers, any requirements for duct insulation, the location and type of fire protection devices, including the fire dampers, smoke dampers, combination fire smoke dampers, and ceiling dampers. And this is something that the building codes require. You know, this information needs to be on the design documents that are being submitted for building permit. And then, of course, details of any offsets required to route ductwork around obstructions, columns, beams, and so forth. So what kind of design considerations are on the engineering side? So, of course, you know, the CFM, you have your static pressure, duct size, fitting types, again, which we talked about. And then that static pressure will end up becoming your construction pressure class. So on the contractor side, you know, some duct construction considerations, of course, you know, the pressure class, which is as specified, the panel width and height. And then with that information, we'll be able to go into the duct construction tables, find our panel thickness, you know, the gauge, be able to select our joint type based on spacings, and then looking at any intermediate reinforcement requirements that there may be. So static pressure versus duct pressure class. Static pressure is the resistance to airflow in the ductwork or other system components. And this pressure is exerted equally in all directions. Duct pressure class, well, this qualifies the duct construction requirements. And then it clarifies the duct sealing requirements. And again, both of these values are determined by the professional of record. So here we're looking at table 1-3. This is static pressure. If you can see my mouse moving around. So the left side of this table, that's, the duct construction pressure class. So this is what you're going to build the ductwork to. Over on the right-hand side, this is your operating pressure. So this is the range of pressure, that the duct system may be operating at. So if you're looking at a 1.5, inch water gauge operating pressure, you're going to look to build it to 2-inch water gauge. And then table 1-1, this is our standard duct sealing requirements. There's 3 classes, A, B, C, and we're not going to get into all the particulars of those, but those are listed in the standard under this table. Dependent variables. This is, you guys don't have books. I'm used to people having books here. So what this is figure 1-2, dependent variables, and you're able to choose the combination for specific system requirements. And first off, maybe you're going with a thicker panel gauge. So this may allow you to have smaller reinforcement sizes, less reinforcements. Let's say, you beef up the reinforcement. You may be able to go with a thinner panel gauge or possibly less reinforcements. And then, say you're adding more reinforcements or shortening that spacing, you may be able to use a thinner panel gauge or smaller reinforcements. And again, these are kind of laid out in the duct construction tables. Just transverse joints. What these are, the joining of 2 duct sections, can be any branch, sub-branch intersection, duct collars, taps, louvers, air terminal connections, and so on. And here we're just showing a couple of typical rectangular transverse joints, drives, plane slips, TDC, TDF, but we're going to get into all the available options in the standard. So here we have figure 2-1. This is the rectangular transverse joints that are covered in the document. And let's dive into a couple of them. Here we have the T1 drive slip, T3 reinforced. This is going to be a gauge no less than 2 gauges less than the ductwork. It does have a minimum gauge requirement of 24 gauge. And it does qualify as a reinforcement per table 2-48, which we will look at in a little bit.
One of the reasons we've laid this table out like this within a new duct construction standard is we found that most contractors, if they made a mistake in their layout and fabrication of ductwork, it wasn't the panel gauge. It was usually taking the transverse joint beyond its usable limit listed in the standard. For example, here we show that you're not allowed to use the T1 drive slip and even reinforced above 4-inch water gauge. So there's some limitations you put, and we thought taking them out of the body of the manual, kind of highlighting them, would be beneficial for all contractors that are working with this. If you happen to use our duct construction app, the unique thing about the duct construction app, if you were to put in the size of ductwork, the pressure classification, if the pressure was high enough, it would not even give you an option to use these transverse joints. It would say, oh, you're at 4-inch water gauge, your ductwork is 60-inch by 24. You're going to be using TDC, TDF. You can't even use this joint. It wouldn't even pop up as an option. So that's where we found people were making mistakes, and that's kind of why we kind of focused on those couple of areas here in the book and also with the duct construction app.
Good deal. Thank you, Eli. Moving on with this one. So this is good up to any length at 2-inch water gauge, 36-inch max length at 3-inch water gauge, 30-inch max length at 4-inch water gauge, and it's not allowed above 4-inch water gauge. Moving on to standing drive slip. This is the T2. You would want to fasten the standing portions within 2 inches of each end and elsewhere at 8-inch spacings or less. Good at any length up to 2-inch water gauge, 36-inch max 3-inch, 30-inch max 4-inch, and not allowed again above 4-inch water gauge. Here we have the plain S slip T5 as well as the T6. Again, this one is not less than 2 gauges less than the duct gauge, 24 gauge minimum. And when used on all 4 sides, you're going to want to fasten that within 2 inches of the corners and then 12-inch maximum intervals. And again, this is only good up to 2-inch water gauge maximum pressure. And as Eli pointed out, this wouldn't even be an option, based on if you selected 4-inch water gauge in the duct construction app. Next, we have the reinforced S slip. This is the T7. You would use S slips conforming to the T6, which we just reviewed. And then you would use a 16 gauge angle, 1x1 height, and slip that into the pocket, fastening with screws at the ends. And this angle can be used for A, B, or C class rigidity. And again, maxes out at 2-inch water gauge. Next up is our T8 double S slip, 24 gauge for 30-inch wide or less, 22 gauge over 30-inch width, and then we would fasten each section of the duct, 2 inches from the corners, and then at 6-inch maximum intervals with 5/8 minimum tabs to close the corners. What I'm showing here is table 2-47, since we were just kind of reviewing flat slip type connections. So this is the unreinforced duct table, table 2-47. And what this table does, it kind of combines all of the unreinforced minimum duct gauges from all the tables up to 48-inch duct width and up to 10-inch water gauge. So once I get into the duct construction tables, I'll show you that column that kind of correlates with this table. And here we have table 2-48. I mentioned briefly when talking about the T1 flat drive accepted as reinforcement. So for this table, based on the duct gauge that you would get from the duct construction table, and the static pressure that you're working with. If you're within what I call the meat of the table, if the width of the duct and the reinforcement spacings work out, then this T1 flat drive would be accepted as a reinforcement. And I'll use this in an example coming up to kind of further explain how it works. Moving on with rectangular transverse joints, getting into our standing S, our T10s, T11, T12. When using on all 4 sides, you would want to fasten within 2 inches of each corner or of the corners, and then at 12-inch maximum intervals. And again, has the same, what I would call limitations as the other transverse connectors we looked at. Good up to any length at 2-inch water gauge, 36-inch max length at 3-inch water gauge, 30-inch max 4-inch, and then also not allowed above 4-inch water gauge. Here we have the T13 standing S. This is bar reinforced. You would follow all of the fastening requirements for the T10 joint, and then the standing portion would be per the T10 or 11. And then you would slide in and fasten the bar stock within that standing portion. excuse me, and connect it within 2 inches of the corner, and then 12-inch maximum intervals. And again, this one has the same limitations as the others. And here we have standing S. This is the T14 angle reinforced. Same requirements as the T10 and the 13 that we just looked at. Although instead of the flat bar, you would use angle. Now we're looking at the T15, T16. This is our standing seam or the angle reinforced standing seam. You would button punch or otherwise fasten within 2 inches of each corner and at 6-inch maximum intervals. Now we're looking at the T21 welded flange. Use a minimum 1/2-inch flange and continuous end weld. Any flanges that are larger than 3/4 of an inch must be spot welded, bolted, riveted, or screwed to prevent separation, 2 inches from the ends and 8 inches maximum intervals. One thing to note, which I have here, is that per the International Mechanical Code, the height maximum would be 1/2 inch for grease duct systems, type 1 grease ducts.
And that also applies to the UMC, because the UMC does reference against NFPA 96 for kitchen grease duct systems, and they max you out at a 1/2 inch flange turnout.
All right, now we're looking at the T22. This is companion angles, Van Stone flanges. You're going to have a 3-inch minimum flange on the duct. And then, the angles must have welded corners. They're going to be fastened, either with tack welds, bolts, or screws to the duct wall, 2 inches from the ends, and then 12-inch maximum intervals. And there's a little bolt schedule down here, 5/16 minimum diameter at 6-inch maximum spacings for 4-inch water gauge or lower. 1/8-inch angles requires 4-inch maximum spacings at 4-inch water gauge, and then 4-inch maximum spacings at higher pressures. Here we have the T22 alternate. Basically, it has, you would follow all the same requirements for the T22. The main difference for this one is you're not putting the 3/8 flange on the duct wall. And then, of course, you want to use a gasket suitable for the specific service and fit it uniformly to avoid protruding, any protrusions into the duct. Now we have our T24 formed on flange. That's going to be assembled per figure 2-17. Closed corners with maximum 16-gauge corner pieces and 3/8 bolts minimum. Lock flanges together with 6-inch long clips located 6 inches from each corner. And then our clip spacings are going to be, based on pressure class. So for 3-inch water gauge or lower, it would be 15-inch maximum. 4, 6, and 10-inch water gauge, we're going to have 12-inch maximum clip spacings. And then, of course, your gasket to form an effective seal. Here we have the T24A. So this is T24 light, if you will. This one is limited to 2-inch water gauge, bolt rivet, 1-inch maximum from the ends, and then 6-inch maximum intervals. And then we're going to follow figure 2-17 for this one as well. So here we have figure 2-17. Corner pieces are not required up to 2-inch water gauge. 2-inch water gauge or higher, you are required to use corner pieces. And again, you bolt, rivet, or fasten 1-inch max from the ends, and then 6-inch maximum intervals. And then here we have the T25A, T25B. This is your TDC, TDF connection. Assembly is going to be per figure 2-18. Ratings may be adjusted with EI rated bar stock or members from tables 2-29 to 2-30. That just means that you can add supplemental angle or exterior reinforcements to kind of beef up that rating or the reinforcement class for that joint. And then single members may be used if they're fastened through both mating flanges, and then gasket for an effective seal. Here we have figure 2-18, which I thought I had a note. We have updated the minimum, the 3/8 bolt minimum. We issued a TRB late last year in 2025, kind of replacing that language with, I don't have it offhand, but per manufacturer's.
It's per the manufacturer's requirements, and you can use either a nut and bolt. You can just use a screw, or we use the term fastener, but it gives you that option now because there are so many manufacturers out there with the proper corner piece saying you can just push through it with a screw. So that is an option you have now based on a technical resource bulletin we issued last year. It's actually up on the SMACNA website in the technical services area. You'll see it there.
So with this one, if you're using clips, you're going to want to have minimum 6-inch long clips, starting 6 inches from the corner piece. And then your clip spacing is going to be based on your pressure class. 3-inch water gauge or less would be 15-inch maximum spacings. Higher than 3-inch water gauge, so 4, 6, 10, you're going to follow a 12-inch maximum spacing for those clips. And clips need to be a minimum of 22 gauge. And of course, screws can be used in lieu of clips. And you're going to start that 1 inch from the end of the corner piece, and then 6-inch intervals for those. Here we have our slip-on flange, your duct mate, 25, 35, 45. So for this one, you're going to want to consult the manufacturer's ratings for the established performance. It is a proprietary product that, has not been verified as an acceptable alternative. But I would caution, if you are going to use a slip-on flange, that's fine. But I would follow all of the duct construction requirements from the tables as far as reinforcement type, reinforcement spacings, and so on. All right, so we reviewed the transverse joints. Now we're going to get into some longitudinal seams that are covered in the documents. The definition is joining of two longitudinally in the direction of airflow oriented edges of duct surface material occurring between two joints. And this does include helic or spiral seams. A little graphic of your longitudinal seams. So for this, we're going to look at figure 2-2, which covers all the seams in the current standard. So we have our L1 Pittsburgh block, pocket depth from 1/4 inch to 5/8 inch. This can be used on straights or duct fittings. Good for positive or negative 10-inch water gauge. Next, we have our L2 button punch snap lock. Good for positive or negative 4-inch water gauge. So if you have any duct construction, 6 or 10, you're going to be using Pittsburgh lock. And then screws must be added at the ends of all duct 4-inch water gauge and at the ends of 3-inch water gauge when the duct is over 48-inch width. Next, we have the L3 groove seam, also called the flat lock or pipe lock. Typically you would see this, on round duct as well, but it can be used as a rectangular seam. And then we have the L1 or L6, excuse me, double corner seam. And both of these are good for positive or negative 10-inch water gauge. Next, we have the L4 standing seam, good for positive, negative 10-inch water gauge, 1-inch minimum seam. This can be used on the duct interiors, and then your fastening requirements are going to be 2-inch maximum from the ends, and then 8-inch max intervals. Next, we have our L5 single corner seam. You would follow all the fastening requirements for the L4. And then next is the T25A, T25B, which can be modified, for longitudinal seam applications, joining large panels or big duct. You can, join that very, very efficiently with TDC, TDF. All right, moving on. So we covered our joints, we covered our seams. Now we're going to look at intermediate reinforcement that's covered in the standard. This is going to be your angle, hat channel, channel Z, and then framing channel or unistrut. And just to note, other structural shapes may be used for external reinforcements when the equivalent effective stiffener rating or that EI rating can be demonstrated. So now we're going to talk about, basic duct construction process. We're going to walk through the steps of, how to go about building some ductwork. So first off, you're going to want to verify the pressure class. Next, we're going to want to check the corresponding table, make sure we're looking at the correct duct construction table. From there, we would start with the larger side. Next, we're going to determine our reinforcement spacing options, and then these can either be a joint reinforcement or intermediate reinforcement. Next, we would check the joint reinforcement tables. Check any intermediate reinforcement tables if applicable. For this part one, we're only going to look at external reinforcement. And the next part, we would look at tie rods options for reinforcements. And then we would repeat for the short side. So here we have the reinforcement tables guide summary. So what this does, this basically spells out and tells you how to read the duct construction tables, and we'll dig into this one a little bit closer. So first off, point out the large rectangle that's kind of encasing the circles here. We have 1, 2, 3, 4 through 10. So basically those circles are column numbers, and there's really no technical merit to them. They just identify each column. Next, looking at, we have the first letter in the table. So hopefully you can see my mouse kind of swirling around there. This is going to be the minimum reinforcement class required. And then the number in the box, that's going to be the minimum gauge based on, the reinforcement spacing that you select, which in this case, we're looking at the highlighted ones, and that's going to be the 8-foot reinforcement spacing options. So kind of digging into the tables a little bit more, if you see a second letter, that is a downsized reinforcement when tie rods are added. So you could downgrade or downsize from an I reinforcement to a G reinforcement we have highlighted here with adding a tie rod. And then down in the lower right-hand corner, we have a KT. So that T means that a tie rod is required for that to qualify as a reinforcement. So kind of summing up what's in the box and the tables. So this one, we have an H20G. This means that the minimum panel gauge is going to be 20. The reinforcement required is an H at the spacing noted at the top of the column. And again, this can be a joint or intermediate reinforcement. And then the second letter, which is the G, means that you can downsize from an H if you use a tie rod as well. And I'll say that I think there's an example that I'll be able to point out. But if to achieve a G class, you're already required to use a tie rod, then that option would not be available. And I'll make sure I point that out when we get into a couple examples here. So what we're going to do is just quickly review what we just kind of went over, looking at a actual duct construction table. This is the 2-inch water gauge, and this is good for positive or negative pressure. Here we have our column headers. The second column in, this is the no reinforcement required. So this column at the gauge shown wouldn't require any additional reinforcements. And again, this ties back to the other table that I showed that kind of correlated all of the no reinforcement required gauges for the 2-inch up to 10-inch water gauge as well. Next, we have our reinforcement spacing options, 10 foot, 8 foot, 6 foot, down to 2 foot. So for a quick example, we have, say you have 24 by 24 duct, you go 18 gauge, no additional reinforcements would be required. But let's say we don't want to build 18 gauge. So we're going to look at, 5 foot joints. So this is saying, hey, we can get away with 26 gauge, but we have to add something every 5 feet. And what this table is telling you, the box is telling you, you need a D class reinforcement every 5 feet to go down to the 26 gauge from the 18 gauge. And then we can look at it further by, going to the intermediate or mid panel. So now we've reduced to a C class, going every 2.5 feet versus the 5 feet. So quickly, I'll just come back to this dependent variables. So what we just went through was a progression of changing variables. So originally, we had our 18 gauge. We looked at adding reinforcements. So we went to the 5 foot, dropped us from 18 to 26. And then further, shortening up that reinforcement spacing down to 2.5, we were able to drop from a D to a C class reinforcement. So this is just kind of the progression of changing variables. And then here we have, I'm just showing, basically your 6 foot would be a 3 foot mid panel, 5 foot, 2.5, 4 foot, and 2, and so on. Okay, so now we're going to look at joint reinforcements. So this is table 2-31. This covers all transverse joints that qualify as a reinforcement, except for the T1 drive. How are we doing on time and questions? Okay. So looking at the table a little bit closer, across the top, of course, we have the joint reinforcement type. What we're looking at now, highlighted in the red circle, upper right, or square, rectangle, sorry, is the T25A, T25B. This is telling us that, hey, for D-class reinforcement, it needs to be a minimum of 26 gauge. So that's the other two small rectangles. The left is going to be a reinforcement class. And then over to the far right is our minimum gauge for that to qualify. And again, this would be based on, the reinforcement spacings that we selected off the construction table. A couple other things to point out. So if you see a plus sign in parentheses, this means that, that option is only available for positive pressure only. If you see a capital R in parentheses, this means that a tie rod is required for that joint to qualify as a joint reinforcement. So now that we've kind of walked through pretty quickly, a bunch of the duct construction tables, how to read them, joints, and so on, we're going to get into an example. So here we have a positive pressure half-inch water gauge system. We have a duct dimension of 26 by 20. We're going to be building 5-foot joints, and we're going to look at the joint type is going to be a standing S and then a flat slit. So what we're going to do, we're going to make sure we're going to go to the correct table. So this is going to be table 2-1, our half-inch water gauge. We're going to check our large side first, which is the 26-inch. And then we're going to, right out of the bat, we can see that if we build it out of 20 gauge, no additional reinforcements would be required. And we could make really any joint length that's feasible. So there's no joint length restriction with this at this gauge. But, most everybody's going to build a 5-foot joint. We're building a 5-foot joint for this example. So we're going to look at the 5-foot reinforcement spacing column. So what this is coming up to is a C26. So we would need a C-class reinforcement every 5 feet, minimum duct gauge 26. So now looking at the short side, the 20-inch, no reinforcement required would be 24 gauge. Our 5-foot reinforcement spacing option is going to be 26 gauge with a B-class reinforcement. Whoops, sorry, jumped quickly on that one. So B class, 26 gauge. So now that we know that from the duct construction table, we need to go to table 2-31, check out our joint reinforcement table. We need to find out, what qualifies as a C class. So what we have here for the 26-inch side are a couple options on the T10, T11, T12. So any of those options would be available to qualify as a C class at 5 foot. Now looking at the T1 drive slip side, excuse me. I mentioned earlier that this qualifies as a joint reinforcement or a reinforcement, I should say, per table 2-48. So now we're going to jump back to that table to see if we qualify. So here's 2-48. We're looking at our short side, which is the 20-inch side. It's a B26. 26 gauge is the column we would look at. And then we can see that up to 20-inch width panel at a maximum 10-foot reinforcement spacing, this would qualify and be accepted as a reinforcement. If we drop down to 18-inch duct, say it was 26 by 18, no reinforcements would be required, and it would be acceptable as well. So our solution for this first example, of course, option 1 would be build it at a 20 gauge. No additional reinforcements would be required. Option 2, we could build it at a 26 gauge, have a joint spacing or reinforcement spacing, I should say, of 5 feet. And then that joint reinforcement for the 26-inch side would be a C class. T10 standing S slip would be 1 by 22 gauge. And then on the 20-inch side, the T1, we could use the plain drive since we qualified that in table 2-48. Hopefully there's anybody have any questions on that one. If not, we'll move on. Okay. So now we're going to look at intermediate reinforcements. So this is table 2-29, and it covers the typical intermediate reinforcement types that are covered in the standard. For struts, we have table 2-30, which would give you the equivalent strut size for the reinforcement class. So kind of looking at this table a little bit closer, what I just wanted to point out, kind of over in the right-hand corner, the lower right-hand side of my screen, it says WTLF. So what that's telling you, that's the weight of that angle or intermediate reinforcement per linear feet. Most people don't realize that, that bit of information is built into these tables, which is pretty nice when you're trying to calculate your, weight for hangers. Some other things to point out. So if you see an H in front of any of the dimensions, that denotes hot formed. If you see a C in front of any of the dimensions, that means that that is cold formed.
And also, just to add on, these are just the typical intermediate reinforcement shapes you can purchase or bend in your shop. If you come up with a different design that's different than this, and you want to try to find out what the reinforcement class is, you can send that to us here at SMACNA. Just email myself or Jeff. All we need is the dimensions of the material you're talking about and thickness of the material and what it is. It's stainless steel. Is it hot rolled or cold rolled galvanized steel? Let us know, and we can go in the steel handbook. It's a very simple calculation to come up with what the EI would be for that, to give you a reinforcement class for that particular shape you guys want to come up with in the shop.
And believe it or not, that has come across our tables quite a bit. People like to build their own hat sections for reinforcements in their shop, and they've sent them through for us to qualify them as a reinforcement class. All right, so now we're going to look at example 2. This time we're bumping up the pressure class. We're going up to 2-inch water gauge, getting a little bit bigger duct here. We're going to look at some 60 by 26, 5-foot joints, TDC, TDF, and no internal reinforcement, simply because we're just looking at external for this first part. So now we're going to jump to table 2-3. This is our 2-inch water gauge table. You want to make sure, you're always looking at the right table, because that has happened before. People have thought they were building it off the right table, and lo and behold, they didn't. So always verify you're on the right table. So now we're going to look at our long side first, 5-foot joints. This 60-inch side is telling us we need an I-20G. And then we could also look at our intermediate or mid panel, which would be the 2.5-foot reinforcement spacing. And that's telling us we would need a G24 in the green box there. So now we're going to jump to our joint reinforcement table, table 2-32. We're going to check our TDC, TDF, see what the minimum requirements are for the I. And that's telling us that it's a 20 gauge with internal reinforcement. That's that R in parentheses. So for this example, whoops, I went the wrong way. We are avoiding internal reinforcements or tie rods purposely. So we would look at the 2.5-foot spacing. That was a G24 from the table. And that's telling us, hey, we need 20 gauge. So you can see the duct construction table said at 2.5-foot spacing, it's a G24. But when you come to the joint reinforcement table, the minimum gauge is going to have to be 20. So that would supersede the duct construction table. And since it's a formed on flange, you would have to build the duct out of 20 gauge. So since we're building a 5-foot joint and we're looking at now the 2.5-foot spacing, we're going to need something in the middle. So on the 60-inch side, we would go to table 2-29. This is our intermediate reinforcement table. And we would select from the G row for any of those, types, either the angle, channel, Z, or hat section, and any of those would qualify as a G reinforcement. For this example, we're going to pick the 1.5 by 1.5 by 1/8 inch angle. And if we jumped quickly to table 2-30, this is the framing channel or strut table that I mentioned earlier, where we could, substitute a framing channel for an external angle or hat channel from table 2-29. So for this one, we would need a 1 3/8 by 1 5/8 12 gauge. So we've looked at the big side. Now we're going to look at, or the larger side, excuse me. Now we're going to look at the short side, which was 26 inches. 5 foot spacing is going to be D26. 2.5 foot spacing is going to be the C26. And again, we're going to jump to our table 2-32, our joint reinforcement table. And we're going to check out what those requirements are. So it's for a C, it says use D. So the D is going to be minimum 26 gauge for that TDC, TDF to qualify as a joint reinforcement. So our example 2 solution is going to be the duct gauge is going to be 20 gauge. Our joint spacing is going to be 5 feet. Or 56 1/4. We're using TDC, TDF as our transverse joint. Our intermediate reinforcement, so that's going to be at the midpoint of that joint, is going to be a G class angle, 1.5 by 1.5 by 1/8 inch. And then the 26 inch side is not going to require any additional reinforcement above the TDC, TDF at the 5 foot spacing. And this is what that solution would look like. The angle on top, nothing on the sides, and our 5 foot joint. Couple notes on external reinforcement. So the reinforcement intervals do not need to coincide. At 4 inch positive pressure and above, the reinforcement must be end-tied. And then that external reinforcement must be fastened within 2 inches from the corner unless tied. And then our maximum fastener spacing is going to be 12 inches. So here's figure 2-11 out of the standard. This is just indicating reinforcement on 2 sides, which is basically what we just went through on our example 2. Same scenario here. When reinforced on 2 sides, again, at 4 inch positive, 4 inch water gauge and up, positive pressure only, end ties would be required. So one of those options would be a 1/4 inch tie rod. And then reinforcements on all 4 sides. This is figure 2-12, just indicating, the requirements when they, when reinforcements on all 4 sides are required. Trying to spit that out. And then the other end tie option would be instead of the angle or the tie rod would be 1.5 by 1.5 12 gauge angle.
And this is different than industrial ductwork where we would be looking at what we call fixed or unfixed corners with the way the angle has to be attached, because in lieu of looking at pressure, which is in our duct construction standard, we're just looking at air flowing through the ductwork and what the pressure is. in the industrial standard, we're looking at not only the air pressure going through, we're looking at the material going through. And instead of calculating deflection, we got to calculate what's called buckling of the panels, which is much different. So the industrial standard will be different than what you show here in the commercial standard.
And then quickly, just kind of pointing out, I mentioned that the reinforcements do not need to coincide. So here you could have 2-foot spacings on your top panel and bottom panel, and then your side panels can have 3-foot spacings. So those do not have to coincide, and it kind of ties into what Eli was talking about, having a fixed or unfixed, reinforcement.
And on occasion, we get this question, usually only a couple, 3 times a year, where maybe the contractor has missed his panel gauge. And per the standard, using TDC, TDF, we said it was supposed to be 22, and they used 24. And they've been called out. What we can do is if you give us the duct dimensions and what you have done, we can show you how to remediate that ductwork that's hanging there without pulling anything down. And that comes into the case of what this slide shows is you might say, okay, you put your reinforcements every 4 feet. Now you got to put one every 2 feet. Even though the panel gauge is wrong, if you do this every 2 feet with an additional reinforcement that might be an 1/8 by 1/8 inch angle, that satisfies SMACNA and would be equivalent to making the right panel gauge that you should have been doing in the beginning. So we run across that, Jeff, maybe 3 or 4 times a year where it does happen. Or you may have come in to do a retrofit of a job, and the design professional said, this system is operating at 3-inch water gauge. Can we get it to 4? And then we could help you do an analysis to say, okay, certain sections, coming off the fan, no, we got to do total duct replacement. But further downstream, yes. Because the duct size gets a little bit smaller, we can probably just go with the existing duct, and maybe we can just add a reinforcement here or there to meet the new pressure class that you're talking about. So those options pop up, whether it's someone got the panel gauge wrong or whether an engineer is saying, hey, I want to bump this system up from 3-inch to 4-inch water gauge as an example. Do I have to replace all the ductwork? And we can look at a couple options for you there. Do that.
Okay, sorry, I was muting really quick to ask a question. So I do have one more example to go through on this part 1. I'm going to skip that due to, to be respectful of time. We have a half hour left, or half hour. So I'm going to skip the part 2 to kind of get into the internal reinforcements and some other stuff that we wanted to cover today as well.
Right.
So with that, if there are no objections, hearing none, no. Let's see. Bear with me. Doing it live is always fun. All right, hopefully everybody can see my screen, and I'm showing part 2. Good. Okay, perfect. So you didn't miss much on the last example. It was just going through another TDC, TDF build, but I wanted to be respectful of time and then, also be able to get some of this other information out there as well. So for part 2, we're going to look at proper tie rod use, and this is positive and negative pressure, procedures for using the TDC, TDF tables, how to fab large duct over 120. We've been getting a lot of this lately. How to convert aluminum construction, which I may, depending on time, kind of gloss over that one. Duct liner, and then double wall duct. I'd like to really focus on the first 3, for the time that we have left. So tie rods, this can be steel rod, can be threaded, unthreaded, partially threaded, conduit, steel pipe. Strap can be used as well under positive pressure applications only. And then very rarely, if any, in the HVAC duct construction standards, you can use angle as well. Here we have this is from figure 2-5, kind of throwing out a couple options for the tie rod attachments. Rod with internal and external nuts, tubing encased rod. And then the middle section, that's going to be probably 99% of the contractors out there using the bolt, machine screw, tubing or conduit with threaded inserts. And here we have just another kind of breakdown of that type. And piping, pipe, tubing, or conduit without threaded inserts may be brazed or welded to the duct wall. So you don't have to use this type of configuration. It may be brazed or welded as well. Here's figure 2-5. These are some other alternatives. You can use a tie rod with a bent foot, 1-inch foot, welded to the duct wall. The bottom two are your strap options. And again, these are for positive pressure service only. And in very, very, very rare scenarios, we have the upper right-hand corner, which would be the G detail, which is a plate with a pretty sizable rod, I guess, if you will. So tie rod attachments, moving on, figure 2-6. So when you're using a tie rod at the joint, it's going to be within 1 inch maximum of the joint. And, these are for joint types, the T21, 24, and T25, unless angle or Z channel is used as a backup.
And in general, for most TDC, TDF applications with tie rods, you're going to have a tie rod on both sides. We did tests years ago with just removing one tie rod. And what we found at 2-inch water gauge, the non-tie rodded side just pulls up too much on a deflection standpoint. So, if you get in a situation, maybe you're dealing with 1-inch water gauge, you could say one tie rod on one side, but it's just not typically done. You're going to be with 2 tie rods on both sides, or tie rod per side, I should say.
Yeah, general application, you're using one at each joint, or 2, depending on how many are needed.
Yeah.
But we'll get into that. So tie rods at intermediate type reinforcements. The thing I want to point out about this one is you're going to, obviously, the tie rod needs to go through that intermediate reinforcement or be tied into that intermediate reinforcement. So you're not going to want to have it off to the side or anything like that. Figure 2-7 here. This is the typical tie rod layout. So upper left-hand corner, you have your, scenario where it's just a MPT, which would be a mid-panel tie rod requirement. Over in the upper right-hand corner, this scenario, we're looking at JTRs and MPTs, so a joint tie rod and mid-panel tie rod requirement. And then the bottom center one, this is, up to duct that's 120 by 120. You would have a single joiner and then 2 mid-panel tie rods. And highlighted in yellow there, all joints must qualify as reinforcements. And, the quantities of tie rods are going to be laid out in the duct construction tables. Some notes on mid-panel tie rods. They can be an alternate to external intermediate reinforcement up to 96-inch 96-inch duct widths, and I believe 6-inch water gauge, and applicable up to 6-foot joints. So you can have a 6-foot joint, 96 by 96, 6-inch water gauge or less, and you could replace a external reinforcement with a tie rod. And again, the transverse joints must already qualify as reinforcements for that to be conforming to the standard. So tie rods prohibited, so you would not use them in underground or under slab applications. Do not use if the air velocity is greater than 2,500 feet per minute. That one there is not because of any structural issues. It's more has to do with noise. And then you wouldn't want to use where condensation can collect unless the penetration is sealed watertight at those the tie rod connections to the panel. Do not use in grease ducts. This is per code. The collection of grease duct and fire is very real with anything inside a type 1 grease duct system. And then if tie rods occur in 2 directions in the same vicinity, they must be prevented from touching or be permanently attached. And this applies to both the joint tie rods, the JTRs, and the mid-panel tie rods, the MPTs. So now we're going to get into an example. So this one's going to be a positive 4-inch water gauge. Our dimensions, duct dimensions are going to be 36 by 24, 5-foot spacing, TDC, TDF. And for this example, we want to use tie rods. So we're looking to use tie rods here. So again, we want to make sure we're on the right table. We check our pressure class. So here we have table 2-5. This is our 4-inch water gauge table. And again, we're going to look at the larger side first. So we're looking at the 36-inch. We have our 5-foot reinforcement spacing, and that's telling us we need an H20. And again, we would look at our 2.5-foot spacing option with the 5-foot joint, and we could drop down to an F26 for this one. So here we would jump to our joint reinforcement table. This is table 2-32. We're going to check our H20 requirement. So for the TDC, TDF joint to qualify as an H, we would need to bump it up to 18 gauge. That's what this table is telling us, even though the duct construction table said 20 gauge, we would need to bump up to 18. And now our other option, we could select the I class with a lighter 20 gauge, but we would need a joint reinforcement. So the I class 20 R is telling us, hey, we can use 20 gauge, but we have to have an internal tie rod at this. That's what the R requirement is. So table 2-5 required an H20. One option was the H18. It's valid because the H meets the minimum requirement, and the 18 gauge is equal to or heavier than the 20 gauge. And the next option is the I20, and that's valid because I exceeds that requirement of the H, and it's valid because the 20 gauge meets the minimum required in the table. But again, we would need to add, a joint reinforcement. So, what if we considered intermediate reinforcement? So table 2-5 indicated an F26 at the 2.5-foot reinforcement spacing. So we'll check that out. So jump back to table 2-32. So an requirement at 2.5-foot spacing. The F would need to be a minimum of 22 gauge. So a couple questions here. Can we use a mid-panel tie rod in place of an external reinforcement? The answer is yes, with some caveats, up to 96-inch, 6-inch water gauge. How many we would need, and then, what size should they be? So we're going to look into all that. So here's our mid-panel tie rod schedule. This is table 2-41. And this is when we would use this table when we want a tie rod to replace an external reinforcement. And again, this table maxes out at 96-inch duct and 6-inch water gauge. So if we kind of dig into the table a little bit more, so we were looking at an F26 at 2.5-foot reinforcement spacing with 22 gauge. So we would go to the proper reinforcement spacing. We're looking at 2.5 foot. And then our duct width up to 48 inches would require one tie rod. So that's the highlighted portion in the middle of the screen there. It says up to 48-inch wide duct, one tie rod will be required with a duct panel of 22 gauge. Excuse me. So now that we know that, we can, and how many are required, we need to determine, what is the load that tie rod's going to see. So we would go to table 2-46. And with this table, we need to find out the load on a tie rod for 36-inch wide duct and 2.5-foot reinforcement spacing. Well, we don't exactly have 36-inch, so we would go to the closest that's not less than. So we would look at the 37-inch, and then looking at the 28-inch reinforcement spacing at 4-inch water gauge. Our load is going to be 154 pounds on that tie rod. So now we know we need one. We know what the load on that is, and we need to size it. So for positive pressure, using EMT conduit, up to 900 pounds, a 1/2 inch will be good, a 1/2 inch EMT. 3/4 inch is going to be 1,340 pounds, and 1 inch is going to be 1,980 pounds. So really most anything that you're going to build in the HVAC duct construction standards is going to fall within this 1/2 inch EMT conduit load range. So now we've checked out the larger side. We're going to now check the short side. So we're back to our 4-inch water gauge table 2-5. So E22 for our 5-foot reinforcement, or a D26 for our 2.5-foot reinforcement spacing. Jump into table 2-32. We look at our D and E requirements, which our 2.5 foot, is going to be a minimum 26 gauge. And then our 5-foot reinforcement, the E22, means that we need a minimum of 24 gauge, but the table is telling us 22 gauge. So our example 1 solution is going to be, we're building the duct at a 22 gauge, 5-foot joints, TDC, TDF. Our intermediate reinforcement on the 36-inch side is going to be 2.5 feet spacing. We would need 1 MPT, so 1 mid-panel tie rod, 1/2 inch EMT, because our load rating is 900 pounds, and we only needed 154. And then no MPT would be required on the 24-inch side. And our other option, we also could have used 20 gauge and a JTR. So a couple notes on negative pressure tie rods. So for these, negative pressure uses special tables. There's different tables depending on EMT, RC, rigid conduit, or just rod. The main concern is going to be buckling, and then shorter lengths are going to be allowed, compared to positive pressure. Table 2-38 covers EMT, and that would be page 2.94 of the standard. So jumping to that standard, that table. So this is table 2-38. So this is where we would size EMT conduit under negative pressure. Kind of looking here at the 1/2-inch diameter. The green box is going to be the maximum length available or allowed at the load underneath of it. So looking to the left of that table, 30-inch would be the maximum length for a 1/2-inch tie rod up to 792 pound load. Oops. And then all the way to the far right. So basically 46-inch max length and 325 pound load would be your limit on a 1/2-inch diameter EMT. So if you had 48-inch deep duct, right away, looking at this table, you're going to be looking at something bigger than 1/2-inch, and we would go down, to look at the 3/4 inch to see what options we had there. So I just throwing that out there as an example. So tie rod loads, table 2-46, which we covered, that's for mid-panel tie rods. And those are going to, take 100% of the load. That's going to replace any external reinforcements. And then there's table 2-34. So this table is used when that tie rod's backed up by either a joint or an external reinforcement. And those solutions are based on 75% of the load, assuming that the other 25% is going to be picked up by the joint or the external reinforcement. And then we have a little conversion down here, 1-inch water gauge equals 5.2 pounds per square foot. That'll make sense in a minute when we go into calculating tie rod loads by hand. So moving into that, so to manually calculate tie rod loads, not using any of the tables, let's say you don't have the tables or you just want to try it for fun, you're sitting at home on a weekend and you want to calculate some tie rod loads. Here you go. So for this one, we have a 48-inch wide duct, 24-inch high, 24 gauge. Our reinforcement spacing is going to be 28 inches. That 4-inch water gauge. So the area is 48 times 28, and that gives us 1,344 square inches. We would convert that to square feet by dividing that square inch by 144. So that gives us 9.33 square feet. So now we would take that and multiply it by the inches water gauge. So we would have 9.33 square feet times 4-inch water gauge times the 5.2 pounds per square foot per inches water gauge. And that would give us a load of 194 pounds on that tie rod. So that's the manual way to calculate your load. And if that tie rod was backed up by a joint or external reinforcement, we would be able to multiply it by 0.75, giving, the total load would be 146 pounds. Do we have a worksheet for this? Yes.
And we'll make sure that worksheet's in the package we send, but here's the worksheet that
Yeah.
Jeff's going to walk you through right now.
Yep. So quickly, I know it's kind of small and won't be able to look at it too much. But this worksheet, you can be used to manually calculate the tie rod loads with no tables. You would just plug in your duct width, your reinforcement spacing, the static pressure, and then the total load, and then the worksheet will calculate it all for you. And the formula for this is W times RS, which is duct width, times reinforcement spacing, divided by 144 times P, which is your pressure, times the 5.2, and that equals your tie rod total load. Any questions on tie rods? Seeing
Just received one in, but we got that squared away for everybody to see on the application of the native tables 2.5 versus our TDC TF tables 2.19. We broke out the TDC TDF and made those separate tables just for ease of use for our members that are just using TDC and TDF as their transverse joints.
Oh, well, that's our next segment.
Yeah.
Is there an easier way? Yeah. So, yes. So the newest edition has TDC, TDF tables. I'm getting the 5-minute warning here. And it's based on pressure class and joint length. So I will get through this one example using those tables here. So we're going to revisit example 1 using the TDC, TDF tables. I won't belabor you with what it is. So we're looking at 36 by 24. We're on table 2-19, 4-inch static pressure. So the thing I do want to point out about these tables, the TDC, TDF tables, is kind of like 2 or maybe even 3 tables in one. You can mix and match between the 5-foot joint side or the 5-foot joint with 2.5-foot reinforcements. But for this one, we're looking at the left-hand side, 5-foot joints. And you can see it easily kind of gives us to the solution, using the native tables that we had to go through a bunch of steps. So now it's saying, hey, for a 36-inch wide duct, you need a minimum 20 gauge with a joiner. Or you can have an alternate joint reinforcement, which would be 2E class reinforcements, and that's an alternate. I just want to point that out. And if we looked at the other side of the table, 5-foot with 2.5-foot reinforcements, we would come to the same solution that we, kind of went through lengthfully on the first example. So our 36-inch side is going to be 22 gauge with an MPT, and our alternate would be an F class reinforcement. And then the short side for this is going to be 26 gauge with an MPT on the 24-inch side. And then again, like I mentioned, you can kind of, mix and match depending on the long side and the short side. So whichever works best for your shop and, which minimizes the need for internal or external reinforcements. You can mix and match between the two sides. So this other solution, if we built it at 22 gauge, we would need a mid-panel tie rod for the 36-inch side, and the short side would not require any additional reinforcements. So, using this one table pretty quickly, we can come up with 4 options out of that one table, if you will. And we just pretty much covered the 4 options, so I'm not going to read all of that off to you again. With the time that we do have left, I'd like to jump over to large HVAC ductwork. This is anything over 120. You would go to figure 2-14. Within that figure, we had table 2-49 that gives you, we'll look at that really quick. Gives you your panel gauge, reinforcement size and spacings. And for any side, that's not above 120, you can use the standard tables in the duct construction standard. A couple things to point out: duct over 120, tie rods are required at every joint and every intermediate reinforcement. So there's no option to not have that. If that was, if you're dealing with a project that you cannot use tie rods, then we would have to go into the industrial duct construction standard. So looking at table 2-49, this is on figure 2-17. This gives us, our water gauge, 1/2 inch up to 10-inch water gauge. This is for positive or negative pressure. Our reinforcement size. So you'll note this in particular, the IT, all of them have the T requirement. So that means that tie rods are required. And then, most are 2.5 foot reinforcement spacings until you get to the 6-inch water gauge and 10-inch water gauge. Then that shortens up to 2 foot. So you're either building 2-foot joints or 4-foot joints at that point. And then your maximum tie rod spacing, is going to be 5 foot until you get to the 10-inch water gauge. And then you're looking at 4 foot. And this would be equally spaced amongst the width of the ductwork. And what I have here is a tie rod schedule sample. This isn't something that's currently in the duct standard, but it's something I built based on, that the previous requirement shown here in this table. And it tells you how many joiners, how many MPTs you need, based on the water gauge and the duct size range. Do we have time for an example, or are we pretty much out?
We could go for a few more minutes, I think.
Okay.
Let's run this quick example.
All right. So if we're building a 140 by 70, 2-inch water gauge, we're going to jump to table 2-49. This table is pretty simple. It's telling us, hey, panel gauge is going to be 18. Our reinforcement size is an IT. Our reinforcement spacing is going to be 2.5 feet. And then our max tie rod spacing is going to be 5 feet. So max 5-foot tie rod spacing. So for this one, we're going to need 2 tie rods across the width at each joint and reinforcement. So we take the duct width, which was 140, divide it by 60, and that gives us 2.33, which rounds down to 2. And then our calculated tie rod width, spacing would be 46 5/8. So that's our equally spaced tie rods across the width. Tie rod load, for this one, we would look at table, we could either calculate it manually like we talked about. We can use the tie rod worksheet, or you can go to the tables and, while it does, max out at a certain size, you can take half of the duct width. So for this instance, it would be 70 inches. And then we could calculate the tie rod load based on a 70-inch wide duct at reinforcement spacing of 28 inches, and then multiply that by 2 once we got that number. So when we jump to table 2-46, we're looking at basically 72-inch at 28-inch reinforcement spacing gives us 146. We would multiply that by 2 to get what the load is for the 140, which is going to end up being 292. Let's see here. Skip.
We're right up against our clock here.
We're up against the clock. So to look at sizing this tie rod, I wanted to show that, hey, 1/2 inch, 3/4 inch, that maxes out at 46-inch and 62-inch respectively. So those would not be options. So for this particular build, we would have to go to the 1-inch, 70 inches, 831 pound load. So this one would meet both the load and the length requirements. And I think this would be a good stopping point to end the slideshow. So I'm going to stop sharing real quick.
As you can see, guys, there's a ton of information. We try to kind of condense as much as we could on the rectangular side, but we've still got a little bit more to go in our next 90-minute session with everybody. And we'll also get into hangers, round duct work, accessory pieces and air distribution systems, flat oval, quite a bit more to go. But if you guys have any questions right now or anything that we can handle, I saw a couple come in through the chat and I think I've got those squared away, but anything else, we're here for you. And if not, you can reach out to either myself or Jeff directly with any questions. Send us an email. It's ehoward@smacna.org or it's gparks@smacna.org. And you get right to us and we'll get you answered up as quick as we can.